Well, the good news is that after Will's talk, we know that software is probably under-tested because software is early. Thanks very much. But I did actually prepare a whole talk, so I'll go through that regardless. I hope you'll bear with me. As was said, by day, I work at Anthropic as a member of technical staff doing a wide variety of research and engineering. And then by night, in my copious free time, I maintain a bunch of open source software. And so when I ask, like, why is everything under-tested, I don't mean why is everything not formally verified. Like, I love a proof-carrying program as much as the next nerd, but it does seem pretty clear to me why not everyone is yet using these techniques. I mean something much more basic. I mean, why, when this community that we're part of, we'll describe this as a small group of weird people, and I agree, but with love, why is it that so few people are using tools like antithesis, or using tools like fuzzing, or using tools like property-based testing that I work on? Because we have a lot of bugs, and like, seriously, we're not even seeing property-based testing in wide use? Can I just see a show of hands? Who here has ever fuzzed some code? That's a lot of people. Who here has used property-based testing? That's also a lot of people. Who here has fully formally verified a piece of code? That's a lot more people than I expected. Welcome, welcome. For those of us who are not familiar with Hypothesis specifically, the main library that I work on, this is a complete executable test using Hypothesis. A counter is basically a multiset. And so we say, given ellipsis instructing the framework to infer from the type annotations what it should generate, if we have a list of mixed integers and floats and we sort the list, then we should have the same count of each distinct element, and we should have pairwise ordering of the output. That's basically the definition of sorting. You don't even need a reference implementation. We should just be able to run this and discover a lot of the bugs in our code. We don't have fancy deterministic hypervisor simulation, sadly. But what we do have is the ability to write things that look just like the unit tests that people are familiar with. And so the barrier to adoption, hopefully, is a lot lower than many more complicated techniques. And does anyone want to guess what happens if you actually execute this code?
It generates a bunch of random input and also focuses on interesting corners.
It does generate a lot of input, focusing on interesting corners. There's a lot of heuristics. There's a little bit of feedback. Not that much, because in a unit testing workflow, people expect it to be fast. And so we just can't afford much instrumentation. Does anyone want to guess whether it passes or fails? It fails with nan. That's correct. Nan is not equal to itself. It's also not less than itself. It's also not greater than itself. And it turns out that this is a nightmare for sorting routines. If you have a stable sort, the behavior ends up being that you have sorted runs between all of the nans. But good luck fitting that property on a slide. And so I don't think property-based testing is the answer to everything. There are a wide variety of techniques that we might use, from things like linters or type systems, which are super cheap and fast. And I'd use them whenever the false alarm rate is low enough. Or we have randomized things, property-based testing or fuzzing, or what happened to my line spacing here? I assume we're all fans of this. Sometimes you have options like invent a whole new tech stack. If you're working on Foundation DB, you can build some really cool stuff, I hear. If you're working on the Firefox browser and you have a lot of memory safety problems, maybe you invent Rust. Basically, if you can possibly get away with shipping a new tech stack, just do it. It's going to be great. Maybe not for your project, but for the world. In practice, for basically any project, you want to pick a mixed strategy across these kinds of techniques that work for your project, that balance the costs and the benefits of these various things. And so I think a big thing that we can do as a community is to build tools that offer people better trade-offs. That we were talking about software being early. Many of these techniques are really young, right? Like usable type systems in production-ready languages are a thing that is not that many decades old. That's happened within many of our memories as working programmers. The idea of property-based testing was first invented in 2000 and really didn't get into its good form, I would say, until like 2010 or 2015. These ideas are not that old. Fuzzing goes back to 1990. My favorite fuzzing paper is, in fact, one of the first ever fuzzing papers by Bart Miller. He just took Unix utilities and piped dev random into them and wrote a paper observing that more than 40% of them segfault. And he's like, look, I'm not going to claim what a Unix utility should do, but it should not segfault. And then he wrote a follow-up paper in 2020, running the same test harness, and finding that about 40% of his original bugs were still there. There's a great footnote which says, like, for some of these, it's fair enough. If you try to fuzz the shutdown utility, your system doesn't do very much fuzzing. But for most things, like, even though these are new, you can pick a mixed strategy, you can do something pretty cool. And so I think the leverage we have as a community of people who are unusually interested in this is to build better tools, offer people better trade-offs, sort of give demonstrations, do advocacy, and so on. And so the way I think about this for Hypothesis is that it's currently used by about 5% of Python users, according to the Python Software Foundation's annual survey, which is great because Pytest, sort of the most popular unit testing framework, is only about 52%. So like that's the level of rigor that we're up against. But then I think there are like three quite distinct axes of ways that you could improve the situation. One is you could get your tools and your practices adopted by more people. Whether that's a culture of how you think about bugs, whether that's the idea of observability, whether that's a particular testing framework, you can get more people using it. Or you can increase intensity. I sometimes say get people to use it more. Sometimes people adopt Hypothesis and they're like, I wrote one test and now I'm done. Back to the old way. And look, you can do that. And often you can get a lot of value out of that first test. You know, there are diminishing returns. But I do think most projects could have more than one randomized test. And the last thing you can do is increase the power. And this is something we often focus on because it's the thing that really benefits us as the developers of these systems. We make it possible to do more interesting, more advanced things with them. And when I think about it, I'm like, gee, 5% of Python users. Am I just like weird in my special interest here? Like, no, I actually think most people who are not using this stuff are wrong, and they would benefit from it enormously if they tried it out. And that kind of brings us back to the adoption piece. I'm like, what is it that I see that they're not seeing that I can communicate? Or how do I make that more attractive? But that was all a bait and switch. This talk is not actually about cost-benefit analysis or making rational arguments. It's not about how do we convince people on this kind of basis. I basically want to emphasize the squishy human factors. Like, why are people not using advanced testing tools? I don't think the answer is they have sat down and carefully evaluated all of the advanced tools and decided that it's just not worth the time to retrain the team. It's just not worth finding more bugs with fewer tests. I think it's actually usually because the ideas are unfamiliar, or they literally haven't heard of it. If you do want to share the ideas with your friends and team, I have a bunch of stickers. Come find me afterwards for those. I saw a tweet some years ago which said, a software engineer is a professional who will do things for a sticker on their laptop that they wouldn't do for $1,000. And I thought, damn, I can get a lot of stickers for $1,000. And so there's this tension where often, I'm developing Hypothesis as a hobby project. For me, it is a fun side project. And in one sense, that really pushes towards engineering rigor in quite an interesting way. Because I know that if I cut corners, if I go quickly, I'm incurring tech debt for myself, which will make my hobby way less fun later. And on the other hand, no one is paying me. I have no customers. I mean, I have a lot of users, but I have no customers. And so I feel very little deadline pressure. And so on the one hand, the business model where it's like build cool software, profit, it's a big question mark when you give it away. But on the other hand, I have this flexibility to really go, how do I make this sustainable for the long term? How do I make this a project that I will be excited about working on a decade later? We just had our 10-year anniversary, and I've been working on it for 8 years, and I just felt my hair going grey last week when I learned that. But a lot of this, when I start talking about squishy human factors, a lot of people are like, come on, Zach, I want to write code. Like, that's the thing I'm actually good at as a professional. That's the thing that I'm interested in doing. And there's good news. I think this is often mocked. But I think that if we take it seriously, often there are technical solutions to these kinds of human and social problems, where changing the way that we build our systems can itself be a kind of social fix. A classic example is error messages. Who here has ever had a confusing error message which led them on a wild goose chase? Yeah, quite a few people. Who here has ever written an error message which led someone on a wild goose chase? All right, and who here has ever been delighted by an error message where their software failed and showed them exactly what they needed to do to fix it? Yeah, that's a much better feeling, isn't it? And so I think this is the kind of thing I'm talking about, the kind of empathy for our users or the people who could be our users. And so I want to spend a while walking through some of the problems that Hypothesis has faced and some of the interesting solutions that we ended up finding to them. So Hypothesis is, I think, probably the most widely used property-based testing library ever developed. The idea of property-based testing was developed in Haskell, and I don't actually know exactly how many users Hypothesis has. I kind of take 5% and I multiply it by the estimated number of Python developers in the world, and then I guess that they're probably drawn from the same population, probably, on average. But if you sort of take that best estimate, Hypothesis has somewhat more users than Haskell does. So I'm still probably in the lead. It turns out a lot of people use Python. And a lot of these people are people who it would never occur to them to use Haskell. As much as I love Haskell, it's very much intended to be a research language, right? The slogan is avoid success at all costs. And that is not Python's slogan. Python is much more willing to compromise, to be pragmatic. When you write a Python enhancement proposal to suggest a change to the language, a mandatory section of the proposal is, how will we teach this? And I kind of love that attitude. It's saying the point of this language is not just to let people get stuff done, to let them build world-scale systems like satellite image analysis, things at NASA, things at Facebook or Instagram. It's also for people in elementary schools. And I've sort of tried to keep that span open for Hypothesis itself as well, even though it's necessarily a slightly more advanced thing in places. So the first problem is that many users just don't read the documentation. Anyone here used a library without reading the docs first? Me too. And often this goes fine. If the library is well-designed in a certain sense of well-designed, often you should just be able to, with some knowledge of the domain, guess what it does. Open it up in your editor and start tab completing your way to success. Or sometimes tab completing your way to not success. And so there are a couple of things that I think are technical interventions which have helped us here. One is error messages. My guess is that something like 1/3 of all the code in a Hypothesis exists to tell people when they're holding it wrong. If we stripped out all of the error handling, all of the that looks weird, all of the you just did something which you really should not have done code, I think the library would be about 2/3 its current size and about 1% its current value. The other one is going for a fairly, what I think of as a low magic interface design. I'm not going to claim Hypothesis is a low magic library. People have complained to me about that before. On the back end, we'll do whatever nonsense we want to find bugs. But on the front end, I want to give people a really cleanly composable set of abstractions. There are times when there are requests, very reasonable requests, a power user feature, an integration with something, a shortcut for something. And I say no because I think it would make the mental model more complicated. It would make the library more powerful. But I think complicating the mental model for the sake of power is, in the long run, a losing proposition. And so I try to draw this really clean distinction between the API, the interface should be clean, the implementation is not. The next problem people run into, if I go to a Python conference and talk to people and they tell me they've heard about Hypothesis and I get really excited. And then, so what do you use it for? And they say, well, I don't. I think it's cool, but I don't actually know how to apply it to my code. Like, you've got toy examples in the documentation. If I was implementing a sorting function, of course, it's very clear what you would do. But, most of my production apps are not, in fact, a sorting service. So it's not quite clear what I should do with my code. And here again, like some of the things you need to do are just writing really good documentation. And shout out to my friend Liam in the audience who is working on hypothesis documentation like a hero. Some of it is giving talks at various conferences, running tutorials. But the ultimate thing that I tried as a technical solution to this problem is a thing called the ghostwriter. If you install Hypothesis, it comes with a CLI app. And you can type hypothesis write and get that app to literally write the test code for you. It doesn't use language models. It uses good old-fashioned AI. And by that, I mean if statements, dictionary lookups, pattern matching, and a healthy dose of type inference in places. If you have a function encode and you have a function decode, the ghostwriter will guess that encode and decode are probably inverses and write a function that tests that they round trip. For a while there, it also thought that if you have a function YAML safe load and YAML unsafe load, that you could load and then unload. No, we had to teach it that safe meant something a little different and unsafe was a whole word. And again, like there's a lot of work on test synthesis out there. And for a lot of it, the goals that the engineers and researchers had was to get great code coverage. And I just think this is the wrong goal. There's a lot of follow-up research which says, yes, you can get good code coverage, and then it doesn't actually help people find or avoid bugs. And so my goal was not to produce complete tests, but to give people something that they could look at and say, yes, that's a test for my code, but I think it's wrong in the following way. And I'm like, great, I've got you over the hump. Now you know what you want to do next. And so again, that's a technical solution. Flaky tests suck. Who here has been annoyed by a flaky test? I hear you all should use antithesis. Because hypothesis, honestly, will not help you if your underlying system is flaky. But the danger of randomized testing is that you introduce that flakiness yourself, right? It's trivial to hook up a test which is powered by dev random or something, but then you run it, it fails, you run it again, it passes, and you're like, did I fix the bug? Or did I just fail to find the bug again? And that's not fun. So we stole a bunch of ideas from fuzzing. Sometimes I describe hypothesis as fuzzing for unit tests to people who like fuzzing. And so the database just records whatever the failure was, or rather it records this sort of underlying sequence of choices that we made to generate that input so that we can replay that later. You can even share that between different people. You can put that database on disk, or you can put it in Redis, or you can put it in any system that can store a byte string key to a set of byte strings values. And it turns out as a field, we've built a lot of those. We have a bunch of replay features so that if you see a failure in your CI logs, you can replay that easily on your local system. And we have what we think of as a deterministic mode, where we set a fixed random seed so that you don't need to worry if you wrote a new test and you merged it onto master and CI was green, and then a new PR comes along and you're like, well, if that's gone red, is that because I introduced a bug? Or is that because my non-deterministic testing system just found an existing bug for the first time? And sometimes people want that, but often they don't. And so Hypothesis lets you split these concerns and say, my CI runs should just say, do I have known bugs? And then I can separately have smoke tests or things running offline in a non-blocking way, which search for previously unknown bugs. Another complaint that people sometimes come with is some bugs are really hard to find. The system's been running for 6 months. We observed a bug once. We wrote a test. We've now been running it for 3 weeks, and we finally found a failure. Could we have found that faster? More often, they don't say we've been running it for 3 weeks and we found a failure. They say something like, the test has been green for 3 years, and then it failed, and we don't know how far back it goes, and it's hard to bisect. Has anyone ever had a really annoying to bisect bug? Few people? Okay. Lucky, we're doing well here. And there are a couple of answers. For those of us who do not have a deterministic hypervisor and fault injection, you can, in principle, do fault injection on people's arbitrary Python code. And if you do, arbitrary things will happen. It turns out people don't love it when you, for example, randomize the shell command before they execute it. In some sense, it's valid. In the other, when you wipe their hard drive, they're not too happy. So we settle for a combination of things. One is in the unit test work case. We have a lot of heuristics. If you ask for integers, we'll spend more time on the endpoints of the range, on numbers around 0, for example. We also support coverage-guided fuzzing. I love fuzzing as this incredibly pragmatic thing. If you're running a single test function for a couple of minutes or longer, fuzzing gives you a speed up over black box testing, which is not measured as a constant factor speed up, but is going from exponential to polynomial search cost. And while it is technically true that for any exponential and polynomial algorithms, you can set the constant so you'd prefer either, you are probably going to prefer the polynomial option in practice. And then finally, just a couple of weeks ago, we finished an integration with C3 for SAT solvers. So if you're using pure Python code, you can plug in a backend. So you can write the test, you can run it black box, you can start fuzzing it, and then you can sit down and in another process, spin up a SAT solver and see if the computer can reason through your code to find any bugs. And I find the pluggable nature of this is fantastic because has anyone just tried applying a SAT solver to testing? Very few people. I'm just going to speculate about why so few people have done that. It's because it's a pain in the butt to harness it. SAT solvers are incredibly powerful. MP-complete problems, usually not a problem for. But the trade-off is that relatively few real-world systems are amenable to being harnessed in this way. You need to be able to translate in some way or have proxies pass through your system that record everything. And so it's kind of difficult to harness. And the net result of that is that often it's unclear whether it's worth a large upfront investment to apply this, and as a result, they're not applied very often. And so that's why I'm so excited to have them as a pluggable backend. It means if you think it was worth writing the test anyway, it now costs you about 30 seconds of setup time to just try a SAT solver and see if it helps. And so I think that could give people a lot more power as well. I assume we have all been in the position where a test has failed, and we look at the failure and it's not clear why. I basically can't solve this problem. Thank you, Turing. But we can do some things to make it easier. One is that when Hypothesis finds a failing input to your test, it will report a minimal failing example. We try variations on whatever caused the failure, and we try more and more variations, and kind of like compiler passes, we'll just go through and iteratively shrink it until we get something so small and simple that nothing simpler we know how to find causes the same failure. Many people have tried building property-based testing libraries without that, and every single one of them I have spoken to says, no, actually shrinking is the key feature. You have to have it. Without that, these libraries are radically less useful. I've also tried fault localization. Has anyone heard of this? 2 or 3 people? Very popular idea in academia, probably peaked about a decade ago. The idea is when your test fails, you point to the location of the bug in the source code automatically. And this sounds incredibly useful. The only problem is, conceptually speaking, it's impossible. Has anyone here ever had a bug or a test failure that was caused by the interaction between 2 correctly functioning components? Yep, those don't have a location in the source code. They have at least 2 locations, maybe more. Has anyone here ever had a bug that was caused by the absence of particular code? Maybe you forgot a case in a switch statement, or you left out some error handling. Difficult to point to code that doesn't exist and say, the problem is you didn't write this code. And so the way I think about fault localization is instead, we want to draw attention to parts of the program that did something unusual in order to help people understand why their test failed. The idea of there is a fault with a location is kind of suspect, but the idea that eventually, at least in principle, we could tell a colleague, this is why the test failed, and it would be maybe a few sentences of prose. And if we can give people information that helps surface that, I think we can make these systems more useful. And then the last one is annotating that minimal example. Right? Suppose you're testing a calculator app, and you just draw some numbers and an operator, and you apply the operator to the 2 numbers. You're probably going to get a division by 0 error. And the minimal example of 0 division error is 0 divided by 0. And if you imagine for a second that you're kind of hazy on what division is meant to do, and you're looking at 0 divided by 0, and like, man, what's the problem? Do I need a non-zero number in here? Is it the denominator that's the problem? Is it the numerator? Annotating the inputs lets you say 0 or literally anything else we tried divided by 0 gives this error. And my experience is in like 30% of the cases, adding this information just lets me read the annotated example and instantly understand what was happening. The other 70%, I'm no better off than before, but 30% of the time this turns out to be really useful. Ever asked yourself this? Why is this so slow? Well, we are in Python. I love it, but... So my 3 solutions here. One is just, do some performance engineering. Some of this is the ordinary, make the code run faster. Some of this is try to be smarter so that we execute the user's test function as few times as possible. There's a sort of useful notion of query complexity. Another is observability. Will was talking about observability largely as a means of understanding the correctness behavior of your system, but I think it's also fantastic for understanding the performance characteristics of your system. And so Hypothesis has support for emitting a JSON logline with all the information we collect about every single test case that we execute. And then you can load that into whatever system you want and analyze it. You can load it into pandas, you can load it into a SQL database, you can upload it to whatever. And start to correlate, is it a particular class of input, a particular size of input, a particular argument that causes my test to be slow or gives me this coverage or causes that failure. And then finally, there's the evil option of make the user's code faster. Most people say things like, Python is an interpreted language. And they're like half right. There's an interpreter. In fact, there's a couple of interpreters. But Python is technically compiled to bytecode. So there is a Python compiler at runtime. But suppose you have someone express, I want any integer. I'll use the integers strategy to generate integers. And then I'll apply a filter, lambda x, 0 less than x less than 10. Does anyone remember what measure of the integers lies strictly between 0 and 10? It's not very many of them. Like, we're talking big ints. They can be up to 256 bits. And there are 9 allowed options, and 9 over 2 to the power of 256 is a pretty small number. But Python code objects also carry some information about the source file and the line number that they were defined on. And so you can go get the source code. And then you can parse out the syntax tree. And then you can do a little compilation step to establish if there are any constant bounds applied. And so you can do things like have arbitrary strings filtered by some regular expression and just rewrite everything in place to be fast. And this is a little evil because it really messes with people's intuitions for what should be fast or what should be slow. But in practice, this makes it radically easier to write things like integrations with database schema libraries. Or for people doing data science who have some sort of schema for their tables, it just means you can very easily translate that into a strategy to generate arbitrary conforming rows or tables. And that enables enough testing that I'm willing to take on some gnarly stuff on the back end. And so hopefully I've convinced you that there's a bunch of interesting technical problems here that we can solve that are mostly aimed at social issues around how do people understand these libraries? How do we get more people to adopt them? And as of the last survey, Hypothesis had just grown 20% adoption in 1 year. We went from 4% to 5%. So that was actually really exciting to me. And you can get the raw data and look at the slower growth curve behind the rounding. But I think these tools are becoming more popular over time. And there's a combination there of more people trying them out, finding them valuable, evangelizing them to their friends. And I think there's also an important trend of we're building better tools. We're building tools that are not just more powerful, but also more adoptable. And so why is everything under-tested? I think it's because historically, we've neglected adoption, relatively speaking. We've focused on power, we've focused on intensity, because these are the things that matter to people who have already adopted the system. And those who are building it have typically already adopted it. I get asked regularly, do you use Hypothesis to test Hypothesis? And yeah, we do. It's great. I'm guessing Antithesis is also used to test Antithesis. Yep. It's great. Why wouldn't you? But I think historically we have neglected to think about what requests will we get from people who are not our users. Who do we not see on our issue trackers and our bug trackers because they're not using the software at all? And how could we extend our concept of what we're doing to include them? Suppose we made an awesome testing framework and no one came from it. Wouldn't this be tragic? And so I also want to say in closing, like, I have no leg to stand on here. Look, I'm sitting down. I'm a hobbyist. I think I'm building cool stuff, and I'm thinking about users. But there have been long periods of time where I thought, well, the biggest thing I could do for a new user would be to work on our documentation. But actually, I would rather work on runtime recompilation of user-supplied functions. And so I did that instead for a while. I've done some other stuff as well, but I don't want to pretend that I'm up here being like, this is the way. I think this is good, and I would like to see us all doing more of this. But I'm certainly not perfect. And so my call is, let's build these testing systems. Let's build our advanced autonomous testing things. Let's build observability. Let's build some of the cultures around testing and software correctness that I would love us to have for the people who aren't using them yet, but who could. Thanks very much.